Yeah, hello. We had some issues that the system didn't like my laptop, and now I have to use a Mac, which I never do, and I hope that works. Yeah, I have this project called badkeys, which I want to tell you about, and I already talked about that a couple of years ago at this same conference, and I have promised not to repeat anything, so if you want more about this, you can watch the old talk, which has other stories about the things I found with this tool. We use public key cryptography all the time. If we connect to a web page that uses TLS, but we have plenty of other things that use public key cryptography. I guess the audience here usually knows what that means. We have a public key and a private key. Usually these days we only use it for signatures. In the past we also did encryption, but that kind of is not ideal and we do something else there. Algorithms we typically use is still by far the most common one is RSA. But then we have a couple of elliptic curve algorithms, and then we have some new stuff which is for post-quantum cryptography. A couple of years ago I started developing a tool that is called badkeys, and is essentially a tool where you can give it a public key or a private key, it supports both, and check if that is affected by any known vulnerability, because there have been a number of cases in the past where software created keys that were not as random as they should be, or there was some way to get the private key back. And I kind of figured that there's not really good tooling for this existing, and if you want to check if something is affected by a very old vulnerability, you're often with, okay, the tools from back then don't work anymore, or maybe they're incomplete, and this is a private key. Can you see why it's not secure?
Too short?
No, that's fine. It's, I think it's elliptic curve thing.
You just showed it to us?
Yeah, exactly. I just showed it to you. So it's not secure. It's also not secure because it's an example key from RFC. But, of course, once a private key is public and recorded on camera and the video is put online, it's no longer secure. So I like to call these public-private keys. Like, for example, if you have something where the private key is on GitHub, I guess we can agree that's not secure, or on Pastebin. So if you're using any of these keys, that's not a good idea. And of course we have plenty of such keys like this on the left. This is from a test from OpenSSL, because of course OpenSSL deals with keys and they have tests, and so they have private keys as part of their tests. But occasionally it seems people need a private key and they don't exactly know what to do, and then they Google for one on the internet and then they find one and use it, and so what I'm currently doing is a project that receives funding from NLnet. If you don't know, they are a Dutch foundation and they are basically funding open source projects for all kinds of privacy, security, internet improvement things. And this project involves basically two things. One is that I just want to have more of these public-private keys so I can check whether people are vulnerable to that. And I want to do somewhat automated regular scans of various sources of public keys that are easily available. So where can I find private keys? There's, of course, plenty of places. There's things like source code. I already mentioned that in the case of OpenSSL, but of course there's a lot of software that has test cases, examples, documentation where there are private keys for various reasons. Of course, there's the internet or the World Wide Web. Like, you have things like blog posts where someone explains something about private keys and there's a private key in there, or they report about a vulnerability or whatever. Plenty of places where you find private keys. And also a very rich source is firmware files, because it's actually quite common that you have device vendors that have a hard-coded key for SSH or TLS that is just part of their device firmware. Most interesting is when they have it as a key which you can use to log into that device. That also occasionally happens. But these private keys come in quite different forms, and if you want to do that at scale, of course you want to automate it, and then you have to deal with all kinds of different variations of keys. And there are things like that. That is a piece of source code. I think could be JavaScript, could probably also be Python, where you have like a private key that is in the source code as a string, and there's some concatenation, so you need a bit of a regular expression to extract something like this. There's also something like this. Anyone knows what that is? No, okay. That's a DNSSEC private key. It's also interesting because, like, it seems there's no specification for this format. I think it was introduced by Bind, and at some point it became kind of the standard. It's used in RFCs, but there's never any reference to a specification. They just, but there are a couple of different private key formats. And ideally, of course, I want all the private keys that I can find, so want to support these different formats. So I ended up like just writing some scripts that support me doing that support extracting all these variations of keys from various sources. And that's publicly available as under an open source license, so in case you also want to use that for whatever. And that I basically use to feed a list of keys of the sort I have that's then used by my tool, so I can use that to find keys that are vulnerable. GitHub has an interesting feature when it comes to private keys. So they have the secret scanning, and this is a bundle of things, but one of the things it does, and it does that by default unless you disable it, if you add a private key to a GitHub repo and try to push it, and this private key belongs to someone else's GitHub account, then GitHub will tell you that. Now, as I told you, I'm kind of collecting private keys, and I'm managing them in a Git repository, and so this occasionally happens. That's how it looks like. They give you an error message. You can then have some way to override that, Then you might be interested then, okay, whose private key is this? You can also find that out. You just need to log in with a shell on GitHub, and then they tell you that you cannot do that, and they tell you your username. So that's how you can figure out this private key you just learned belongs to some GitHub user, who it is. Usually when this happens, then I look up the profile, and it's usually some kind of, someone who hasn't done much on GitHub. Maybe there are a few test repos, but it's not very interesting. But sometimes it's different. For example, at some point I found the private key of a developer from SUSE Linux, and then a few days later, the private key of another developer from SUSE Linux. Of course, I did responsible disclosure and reported it to them, and DNSSEC. I had included that because I was working on it while at the time I submitted the talk. I'm not super familiar with DNSSEC, but it also uses public key cryptography to sign DNS records, and it's actually quite easy to get these keys in large quantities because A, you just need to query the right DNS record, and B, DNS is very fast. The result was kind of boring. I only found like 2 hosts. They were using an example key from an RFC. Yeah, that was it. So not many findings, but yeah, I scanned for that. DKIM. There are a few more fun stories here. First of all, one that is not really a security issue, but kind of bizarre. So DKIM, I guess also most people will know that it's a kind of email signature system where you can sign an email and then you can put the key on a DNS record belonging to your domain and kind of have a connection that you're showing that you own the domain that you're sending your email from. And this is one of the keys, how they look in DKIM. So it's a TXT DNS record. And you may wonder, of course, here's some base 64, but what kind of key format is this? Legit question, right? Needs some kind of specification for the format. If you read the RFC for DKIM, it says so if it's an RSA key, they only support 2 types of algorithms, but for RSA is the common one. The RSA key type indicates that an ASN1 there encoded blah 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 RSA public key C RC3447 is being used. RC3447, I happen to have written my diploma thesis about it, so I know what that is. That's also called PKCS1, is kind of the original RSA standard. But then later in the specification, they show an example how you create such a key with OpenSSL. Except it's not, because if you use the command they use here, then you get a key in a different format, which is called SPKI, which is specified in a different standard. So you have a situation that the DKIM specification says you should use PKCS1, but it uses SPKI in an example. The reality is that it seems the internet has agreed on using SPKI, and just nobody noticed that the spec says something different. So I recommend you do not follow the spec, because it will probably not work. Yeah, but yeah, I wanted to scan for DKIM keys, and there's an issue with that, and that is you cannot just get the DKIM key for a domain, because you need something called a selector, which is just a string, and that is like in the signature within the mail, you have this selector string, and then you fetch the key by doing selector.domain name. You can only do that if you have the selector. What can you do? One option is you get a lot of emails, and one option for that is there are some mailing list archives, for example, the Linux kernel mailing lists or the IETF mailing lists. You can just download them, and then you can extract many selectors from these emails. Another option is also, and that turned out to be more effective, you can just brute force them, because this selector is basically an arbitrary string, but many people will just use key, DKIM, key 1, something like that, and I just figured out, okay, there are, like, I think I used 10 common selectors that just many people use, and then you can collect a lot of these DKIM keys. Yeah, so what do you find if you check them for security issues? There was a vulnerability in XIM, like the XIM email server, in 2016. And what happened there was that under certain configurations it would write a private key to a log file, and there could even be a situation where this private key was leaked in an error message. So 2016, so that was a while ago. But XIM, in their documentation, they have a text file where they describe this vulnerability and explain it. And in this security advisory, they show an example of that. So if you're affected by this issue, you can check your log files. It looks like this. So yeah, private key in the log file. So that's another public private key, like the one in the advisory with the example from the log file. And actually that one was still in production until quite recently. I have no idea what happened there. I reported it. I didn't get an answer, but they removed it. Anyone remembers this CVE? That was the Debian OpenSSL bug. You probably remember that, except if you're maybe too young for it because it was 2008. So, quite long ago, Debian had a vulnerability where they had a patch for their OpenSSL package, and that basically broke how their random number generator was working, and you ended up having only a few tens of thousands of possible key combinations that OpenSSL would generate on these vulnerable systems. And of course, badkeys can detect this vulnerability. Last year, I did a scan of the Tranco top 1 million list with for DKIM keys with this, as I told you, with this brute force method. And from I found around 350,000 valid RSA keys, and of those, around 800 were vulnerable to this Debian OpenSSL bug from 2008. Which is quite a significant number for a 16-year-old vulnerability. What's maybe even more interesting is some of the domains that were affected. I think some of these are kind of larger companies. Yeah. And I speculated a bit, why did that happen? And one thing that kind of stood out is that this DKIM was first published within the time frame where Debian had this vulnerability. So, because this vulnerability was introduced by a broken patch in 2006, and in 2007 DKIM was published, and in 2008 they found this bug. So my assumption is just, okay, there were apparently a number of people who configured DKIM right when it came out and never changed their keys since then. I tested this, I thought, okay, now I have a DKIM key from Dropbox and Shopify and whatnot, and can I write an email to myself with their sender domain? And yeah, that worked. And then I saw these nice logos, and these logos, that is something called BIMI. And BIMI is it's kind of an extortion racket. Like they say, if you want a logo like this, you have to pay us a lot of money. One of the companies who's selling this is Entrust. They are the one with the logo up there, so they were also affected by this. I gave a longer talk about this whole DKIM, Debian OpenSSL thing at another conference, and have a dedicated webpage for it. So, feel free to also watch that if you want to learn more about it. Earlier this year, there was an incident with Fortinet FortiGate devices. So in 2022, there was a vulnerability in these devices where it was an authentication bypass, so I think you could log into their management console or something. That was known, and it was also kind of known that this was exploited. So there's a press release from FortiGate from 2022 where they say, yeah, we know there's active exploitation going on of this vulnerability, please patch. And earlier this year's configuration files from 15,000 of these devices were published on breach forums, which is, I think it's no longer online. It was some kind of underground leak sharing forum. These configuration files contained private keys for TLS, for SSH, and I think for some other things, but they were encrypted with a password. Password was also in the configuration file, but also encrypted with another password. But that other password is static and publicly known. So, yeah. you just need to decrypt the password and then decrypt the key with the password you just decrypted. And it turned out from these keys, there are still around 100 keys for TLS certificates that were not expired or revoked, and around 300 keys for ACME accounts. Like ACME is this automated certificate issuance protocol from Let's Encrypt. So, and remember, like, this was known since 2022, so it appears the people using these devices were not acting on that in a meaningful way. I guess that's enterprise security. Yeah. Last year I also gave a talk at the OWASP Day where someone came to me and asked if I had looked at OpenID Connect, because that also apparently uses public keys. I had not, but did after that. So OpenID Connect is this thing where you have single sign-on, like you have a web page you can log in, and then you can say, I want to log in with my Google account or something like that. The protocol behind that is usually OpenID Connect. And if you're a login provider for this protocol, then you can publish a configuration file which your I don't know how do you call it exactly, your consumers of your service can use under a certain specified path. And this configuration file then contains a link to a JSON web key set, which contains public keys that you can use to validate the login token or, yeah. These JSON web keys have a very interesting property. So here you can see a public key and a private key in JSON web key format. What you may notice is that they look very, very similar. The only difference is that the private key contains an additional value. What that means is if you use the private key instead of a public key, it will still work because it's the same file format. So, yeah. So you have the same format for public and private keys. As a kind of security person, I get interesting ideas when I hear something like that. I mean, nobody would confuse a public and private key, right? Or maybe they, yeah. Yeah, so I did a scan of OpenID public keys. And yes, I found a couple of people using their private key as a public key. I also found a couple of setups that were using example keys from OpenID Connect libraries, like where the private key was part of the software they were using. And I found a couple of RSA keys with 512-bit, which is something you can break with publicly available software in a few hours. Yeah. That was it. Thanks for listening. If you do any kind of security work, you may want to use badkeys to, I don't know, if you do a pen test or something and you deal with any form of cryptography, check the keys. And also if you feel you may need someone who, I don't know, who knows something about private keys, please talk to me. And also, I said I'm currently sponsored by NLNet for this, but this is gonna run out by the end of the year. And if anyone thinks, hey, you should really regularly scan these types of keys, and I want to sponsor that, please also talk to me. Yeah, thanks. And I think we have some time.